I'm going to view df as a machine that I construct from a function that accepts an argument and returns a number.
Mm-hmm.
And if you're confused by the red notation, switch over to the purple notation, and we'll watch Mathematica actually do it. So complete and consistent, because Mathematica has no intuition or imagination at all. All it's going to do is follow with the utmost literalness all of the rules that we've set. So eventually, we're going to show Mathematica expressions like this. There'll be a coordinate symbol here. It'll be wrapped in a V to associate it with a vector. There will be a function here constructed out of coordinate symbols. And it will be wrapped in a D to indicate that it's a one form. The proximity of these two kind of functional brackets will indicate that this is a one form applied to a vector. And Mathematica knows enough of calculus that given a symbolic expression for a function, Mathematica can evaluate this partial derivative. In fact, what Mathematica writes over there is given any input. So this is a pattern that matches any input. Take that input, feed it into a pipeline, replace all, meaning everywhere in the input. So this pound is a temporary name used for whatever came through the pipeline. Take whatever came through the pipeline, look everywhere inside it for this pattern. You could put several patterns here, but we're only going to put one. Look for a D wrapping around any argument that I'll call argument 1. Look for it to be followed by a V wrapping around any argument 2 that is a symbol. When you see that pattern, replace it with the derivative of argument 1 with respect to argument 2. So that's a very explicit instruction, and an example of that would be, let's take the exterior derivative of the function sine of x over 2 with respect to the basis vector associated with the symbol x, and feed it into a pipeline that consists of process forms. Mathematica will say, well, here's the input. Here's a string that matches this pattern. I should replace that with the derivative of sine of x over 2 with respect to x. And Mathematica knows what that answer is.
So that big D is actually a...
All of these are built-in Mathematica functions.
So that is actually an operator in Mathematica that will evaluate the derivative.
Yes. And so this will return 1/2 cosine of x. And this is how we actually do differential geometry in Mathematica. There's almost nothing more to learn than this. We're just going to put these pieces together. So here we have a function, which is a zero form. It's operated on by an exterior derivative. And an exterior derivative of a function returns a one form. A one form is a machine that, given a vector, returns a number. And at the point labeled by x, the number that it returns is 1/2 cosine of x.
Mm-hmm.
So now, given any point on the manifold, we can evaluate this one form and this vector together and get a number.
Mm-hmm.
Okay? Now, it may not be so obvious how, we still seem kind of a long way from these pretty pictures,
Mm-hmm.
but this is how we put flesh on these abstract bones.
Mm-hmm.
I'm going to do 2 more rules to get us used to this idea of rules. But then it's not crazy to look among books for differential geometry or even look on Wikipedia for discussions of vectors and one forms and to deconstruct how this whole thing goes.
Mm-hmm.
Because in the most literal way, this defines how one forms and vectors work.
Mm-hmm.
So here comes one. They're always talking about vectors. So what we need is some rules like this, that D, acting on any function of coordinates, if I give it a v of x plus b v of y, remember, a vector space has the property that you can multiply vectors by numbers and you can add vectors together. I want a rule that says that that is equal to d f of theta acting on, well, a, I'll put in a times here, df of theta acting on v of x, plus b acting on df of theta v of y. I want Mathematica to recognize that if I have sums of basis vectors, that I can pull that apart and into a form where, once I get it to this form, this rule kicks in.
Uh-huh.
So I'm just teaching Mathematica that the vector spaces are a linear space.
Mm-hmm.
And there is a little rule there that I write in a very abstract form. One forms are a vector space too. So if I have D acting on F1 of theta plus D acting on F2 of theta, that sum is itself a one form. And so if I act on a vector v of theta, then I want a rule that tells me that this is d f1 of theta plus d, it's very tedious to write all this stuff out, df1 of theta, v of theta, plus d f2 of theta, v of theta. And again, this form, Mathematica doesn't know how to simplify, but these two forms, Mathematica does know how to simplify. So the way you actually conceive this stuff is you start trying to do calculations, and things that you would do by hand if you were doing it by pencil and paper, you write down as rules for Mathematica to implement.
Mm-hmm.
So is there some general rule that would generalize this? How would we write this particular calculation in terms of patterns? That pattern would be this. arg1, arg2, Okay. Underlines are Mathematica's pattern. V of theta means theta is anything that's a pure symbol, not some complicated expression.
Mm-hmm.
Arg2 means any single expression not separate, not including a comma. Arg1 underscore underscore means one or more arguments separated by commas.
Mm-hmm.
And wherever we see that, we write that as plus arg1 acting with, on a vector plus arg2 acting on a vector. That doesn't seem to buy us anything, but actually it does. If arg2 is a 1 form, then this second part of the expression will get simplified. And not only that, if arg1 has more than one argument to it, this rule will fire again. And the last slightly tricky thing is this. Equals is in Mathematica usually associated with a definition. Colon equals is associated with a definition that's evaluated at runtime.
Mm-hmm.
Caret colon equal is called an up value. Mathematica has to associate this rule with some symbol, and you're not allowed to change the definition of plus.
Uh-huh.
Because that leads to bad things.
Uh-huh.
So up value means look at the left-hand side, and any pure symbols at level 1 associate the definition with them. And if you work it out, there's only one symbol at level 1, and it's V. This rule is something that Mathematica fires whenever it sees a V.
Mm-hmm.
So in the lingo, this ensures that vectors distribute over addition.
Uh-huh.
And of course, this is the usual thing. This is the familiar thing in calculus. D by d theta of f1 plus f2 is df1 d theta plus df2 d theta. These are just the ordinary rules of calculus written down in symbolic form for Mathematica to apply. So it's very useful to kind of screw around with these a little bit. Mm-hmm. And if you check a little, well, now I have to tell realistically how I evolved these. I set out to do problems where I knew the answer, and originally Mathematica would produce indigestible hunks of algebra that I would simplify by hand. Wherever I had to simplify an expression by hand, I would ask, what rules of calculus am I using? And then I encoded those into Mathematica in the most general form that I could conceive. And there turns out to be exactly 7 such rules. And not by accident, they're the same rules that you'll find in every introductory chapter of every differential geometry text. Mm-hmm. So the only thing that Mathematica forced me to do was to state all of those rules explicitly with no sign errors. Mm-hmm. So they are complete, and I will even assert with reasonable confidence that there are no sign errors. So the bad news is there's about 5 pages to go all the way to the happy picture of the donut. And the good news is there's only 5 pages to go all the way to the happy picture of the donut. And this is the single hardest page. We're just creeping up on the hardest thing of all, the wedge product. Mm-hmm. Up to this, I do the XY plane, I do the ZZ bar plane, mm-hmm. And then when I look at the intermediate results, I can understand everything that's going on. Mm-hmm. And I actually didn't write this code and solve the hard problem first. I worked out these rules with lesser calculations. So here goes another guy thirsting after knowledge. Would you like to learn differential geometry in 90 seconds? It will take you 2 minutes if you want to do complex coordinates.
He wants to just set up a projector.
Oh, a group as big as yours, just go ahead and assail us here. Just go on in, dude. I mean, say, for example, well, I'm not really interested in thermodynamic equilibrium so much as I am in the ground state.